a parallelogram. Two equilateral triangles come together to equal a rhombus. Two isosceles right-angled triangles come together to equal a parallelogram. Two right-angled isosceles triangles come together to equal a square. Two right-angled scalene triangles come together to equal a parallelogram. Two right-angled scalene triangles come together to equal a rectangle. These guys are all right-angled scalene triangles. If I join their short sides together, they end up with a parallelogram. If I join their middle sides together, I end up with a parallelogram. If I join their long sides together, I end up with a rectangle. These two are the same, both isosceles right-angled triangles. Can you see if I join their short sides together, I end up with a parallelogram. I could do it this way or this way, it's the same deal. Long sides together, I get a square. The long sides together, a rectangle. Long sides together, I'll get a square. A triangle that has got three equal sides can be joined this way and it is a rhombus, but equally this way or this way, and it's still a rhombus because they're all equal. So that's the rhombus. Does this make sense to you? And this is how you create a trapezium out of triangles. Can you see that? It is made out of a scalene obtuse angled triangle and a right-angled scalene triangle. Does that all make sense? So that idea of triangle, we're starting DCE. This is how fast it goes. We're just working at a different speed limit. Jolly good. So you'll see me do that.
I have a question.
Yes?
Is there any specific reason for the colours?
No.
Okay.
Because there are no colours here. It's the same pieces of material, but you're able to join them now without the black lines, and you can create shapes. There's a new shape. What's the shape called? Two right-angled isosceles triangles together can make a right-angled isosceles triangle. Okay? This one goes together with this one. You can see, you've seen this shape before, which was a
rectangle.
Rectangle. You've seen this shape before as a parallelogram, and this shape before is a parallelogram. You can see these two before, which we know is our rhombus, and these two just can fit together to make your trapezium, which is okay, trapezium. Jolly good. Got it? So that's the second constructive triangle box. The first constructive triangle box has colours and the black lines as indicators. The second, all of those clues that go on the chart can now do a free exploration of that. The third triangle box is actually a triangle box, so I'll show you the triangle. Should be able to put these away beautifully. Okay, you guys have done fractions already. Let's have a look at some of this work here. If this is a whole, then this could be two halves. Yes, easy? Nice. And this could be 3/3. Yes, and this could be 4/4, right? So this is a quarter, and this is a third, true? And this is a half. Got it? Nice?
Yeah.
What is this shape called? Cool. Can you start to see how every shape can be cut up into triangles? It's quite an important understanding about our world that you understand this concept, because it gets a little bit more complicated, as you might imagine. This is an EC material, but we use it quite differently. Here you'll see a triangle, a
Rhombus.
A
Trapezium.
Cool. And a pentagon. That's pretty cool. But we can also see that this shape is also a, what shape? The shape is?
Huh? Oh, a hex. Not. Yeah, I
Three,
am right.
four,
A
six.
hexagon, right?
Yes.
So this tells me that if I cut it into, what's this shape called? Obtuse angled isosceles triangle. If I cut it into obtuse angled isosceles, I actually get 6 obtuse angled isosceles, which is actually the same as 3, what are these called? What shape are these? Which are the same as these rhombi, right?
Yes.
Yeah, they're exactly the same. Or, so I could cut it up like this, boom, boom, right? Or I could cut it up like this into hexagons. Or I could cut it up like this and still have the same 3 rhombi, but just cut up differently. Okay, these are equilateral triangles. These are. So give me some fractions now. What fraction is this
One.
of this? Half. Yes? This is a half of the hexagon. This is how much of the hexagon? Can you see it there?
Yeah.
So you're telling me these two are the same?
Yeah.
Yeah? You sure?
Yes. Yes. No.
The area.
The area is the same.
Is the area the same?
Yes. No. Why?
This is half of a hexagon. True? Yeah? That green on this. True?
Yeah. Wait, what? You said the green one.
Can you see that shape there is half of a hexagon?
Oh, yeah.
And this yellow is half of a hexagon.
Oh.
Is it half? Is it half? It's the same there? Yeah.
Oh,
So this is half of a hexagon and that's half of a hexagon and hexagons the same size. What does that tell me?
It's the same.
Cool, right? That's
Yeah.
logic. We're going to get into upper logic. This is
Okay.
all about logic. So if this is the same area as this, true? Yes. What is the relationship between this piece and this piece?
They're both,
Why?
they're both 1/6
Why?
because they're a third of a half.
This is a half, totally, and a third of it is this piece, which is a sixth, right?
Yes.
This is a half of the total,
Yeah.
a third of it is 1/6. You're telling me these two are the same?
Yes.
Totally the same.
The same area.
Yeah? See how it works? But they look quite different. But we could say that this is a third, a sixth, and this is a sixth of this particular game. Yes, 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 yes. Really. What is the relationship between this and this? I wonder, is there a way that we can find out what the relationship is?
2/6, 1/3.
You're saying that this is 2/6, yes? Therefore you're saying this is 2/6, therefore you're saying this is 1/3,
Yeah.
right? So if this is the same, this is 1/3 and 1/3, right? This is 2/3. So this is 2/3 of that
Half.
hexagon, right? So if this is the whole hexagon, this is 2/3 of it, right? So therefore 4 of these should equal this. How? Can I get 4 of these to equal that? Spot this. Start to see now? There are so many different relationships. Rather beautiful question. What is the relationship between this and this? Same shape, different size. You need to spend quite a lot of time playing with this material to find that out. But it's a really nice question. Okay? We found lots of relationships so far, didn't we? How's your brain?
I never understood shapes before this, and now I'm like,
You're going to get
I
this.
actually really like shapes now.
So cool. It is so cool. So you've got some work to do because there's a challenge. I want to find out the relationship between this. And I just want you to tell me. I want you to show me without any words. Okay? This is called logic. And if we believe the rationalists that logic is a human endeavour and the highest and purest of human endeavours, then actually it should be part of education. The ability to think abstractly. There's a beautiful set of shapes in front of you. How do they all fit together? What are their relationships? Yeah? And then there's another whole box of a whole lot more. And so it goes on. What are the relationships between each of these to each of these? What are the relationships between these two triangles? Between these three triangles? You actually already know.
They're all the same,
They're the same. Mate, they look different to me.
okay?
Don't they look different? Don't they look kind of different? What is the proportion of this to this? I actually just showed you, but anyway, you guys can find it. All right? Yes, something to chew on?
Yeah.
Nice. Constructive triangles are an enormous amount of fun. I like them a lot. You're going to put the 4 reds at the bottom, then you're going to put the 3 yellows, then you're going to put the 2 greens and the grey on top. You got it? Show you. You're going to put the red at the bottom, the grey on the top, the yellow on top of that. That would be good. Yes.
Like red in the bottom, then
Not that yellow.
Red.
Red, grey, yellow.
Yeah.
red, grey.
Because now the yellow there goes to
Hexagon, hexagon, triangle, triangle.
That one going over that way.
There you go. That one's all in there. That one's all in there. That's all in there. That's all in there. All right.